For decades, the surgical microscope has been the standard in visualization for ophthalmology. While effective in providing a crisp visualization, the microscope affords only a limited field of view and tethers the surgeon's head to the microscope. This is beginning to change, however, with the introduction of new technologies into the operating room, such as the 3D TV shown here. 3D TVs free the surgeon from the microscope oculars, yet still provide only a limited field of view. Similarly, heads-up displays integrated into surgical microscopes provide additional information through the eyepieces, yet still tether the surgeon to the oculars. Augmented reality displays, such as the Microsoft HoloLens, provide a potentially unlimited field of view by tracking the wearer's head within a 3D environment. Unfortunately, optical feed-through techniques, in which additional data is overlaid on the wearer's normal vision, suffer from limited display contrast and limited eye field of view. This brings us to virtual reality displays, where not only is the wearer's field of view unlimited, but the display device is in complete control of their visual inputs. VR consequently offers unparalleled display opportunities, but this comes at a cost. The control software must meet aggressive rendering requirements to avoid causing motion sickness. Frequently, this means rendering at up to 90 frames per second for each eye. This paper describes GPU approaches and data organization techniques for high frame rate raycasting necessary to bring volumetric OCT into immersive VR. We constructed our virtual reality OCT viewer using 3 scene elements. First, we provided a wireframe floor as the background. This helped keep the immersed user oriented as they navigated the virtual environment. Next, we overlaid the OCT volumetric render over the background. Finally, we drew the VR controllers that allowed the user to interact with the volume. Raycasting OCT volumes in real time at virtual reality frame rates required careful optimization of the volume's layout in GPU memory. The volume is essentially a large 3D array of OCT intensity data. This array can be visualized by the grid of green rectangles on the left-hand side of the screen. Each block represents a 32-bit floating point intensity measurement. As rays propagate through the volume, they query the intensity at their current position to determine that voxel's contribution to the final image. Each query results in trilinear interpolation between the voxels forming the cube that bounds the sample point. This is illustrated on the right, where the red circle indicates the sample point and the 8 green cubes represent the voxels that participate in trilinear interpolation. Thus, each intensity query results in 8 lookups into GPU memory. Raycasting algorithms also compute the gradient at the sample point and use it to shade the volume structure. The gradient is estimated as the finite difference across the sample point in the x, y, and z dimensions. This results in 6 additional intensity queries, each of which require 8 lookups into GPU memory to perform trilinear interpolation. Thus, directly storing the OCT intensity in GPU memory consumes 4 bytes per voxel and requires 56 memory lookups for each raycasting step. These repeated lookups degrade GPU cache performance and subsequently slow down rendering. Fortunately, we can reduce the number of lookups by noticing that the volume is rendered much faster than it is acquired. We can exploit this by pre-computing the gradient and interleaving it with the intensity in GPU memory. This not only reduces the number of memory lookups from 56 to 8, but also eliminates the gradient computation. Although this quadruples the size of the volume in GPU memory, we can switch from a 32-bit floating point type to an 8-bit integer type and thus restore the volume's original memory footprint. We can do even better, however, by collecting the 8 corners used in trilinear interpolation and packing them into a single texture element. This comes at the cost of doubling the volume size and memory, but allows us to both trilinearly interpolate the sample's intensity and compute its gradient with a single memory lookup. With these last 2 configurations, we can render the volume in real time at VR frame rates. With that introduction out of the way, let's pick up our VR controllers and see how this works. With one controller, the user can pick up and move the volume around. By using a second controller, they can rotate and scale the volume. Using buttons on the controller, they can activate cut planes and move the volume through the cut planes in real time. Multiple cut planes can even be activated simultaneously. We can apply these same techniques to live volumes as well. Here the immersed user watches as a needle is inserted into a porcine cornea. With careful placement of cut planes, the user is able to reveal the needle bite depth. Using the VR controllers, the user is able to rotate the volume as needed to obtain an optimal viewing angle. We can even use OCT from within VR to guide mock surgical procedures. For this application, we provide external video feed-through to keep the immersed surgeon oriented. Because the surgeon's hands were occupied with surgical tools, we provided an external operator to manipulate the OCT volume on behalf of the surgeon.